So let's look at how we can represent numbers in binary on a computer. And this here we were talking about an 8-bit, that's key, how many bits we have, signed number representation. And so we have different signed number representation. We have signed 2's complement, signed 1 complement, and signed magnitude. It is true that signed 2's complement is primarily what's used in computers, but we'll look at all of them. So if we wanted to represent the number 17, it's a positive 17, so in all number representations, it's going to be the same number. So the number 17, that's 16 plus 1. 16 is 2 to the 4th, right? So we got 0, 1, 2, 3, 4. This is going to be our 1. That's going to be 16, plus 1 will give us 17. So you can verify this. And that's a 17 in binary. So I'm just going to repeat that. 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1, right? So in all number systems, positive 17 is going to be the same. So that's the key idea. So what we did is 2 to the 4th plus 1, and they're all the same when it's positive, right? So when it's positive, additionally, this most significant bit, that's our sign bit. So our sign bit here is a 0. A 0 indicates positive, and that's a 0 in the MSB sign bit. So if we want to do negative 17, let's start over here on the right now. In sign magnitude, all we're going to do, instead of using a negative sign, which we can't just do that on a computer, right? We're just going to convert that to a 1, and everything else is going to stay the same. 0, 0, 1, 0, 0, 0, 1. Signed 1's complement, we're just going to take the 1's complement of the number, right? So if we take the 1's complement of the number, we're going to flip every bit. So that 0 becomes a 1, 1, 1, 1. That 2 to the 4th 0 becomes a 1, 1, 1. And note here what we end up with in our sign bit, that's a 1. This is a 1. They're negative. For our 2's complement, we can just do the 1's complement plus 1 if we want, but so that first 1 remains the same, and then we flip every other bit. 1, 1, 1, 0, 1, 1, 1, and again, our sign bit, all our sign bits are a 1. So that's a key idea. 67, how are we going to represent 67? So our 67, that's, 2 to the 6th, that's 64. So we need that plus 3, right? So if, you can get to it how you want, but so all of them are going to be the same. That's going to be our 3, and then 2 to the 6, 0, 1, 2, 3, 4, 5, 6, that's a 1. And our sign bit is going to be a 0. So for all of these, our sign bit will be a 0. For all of these, it's just the rest of them represent a 67. 0, excuse me, that's a 1, 0, 0, 0, 0, 1, 0, 0, 0, 0. And then, I'll let you do the same thing, for negative 67, for the signed magnitude, that just becomes a 1, and the rest of them all remain the same, right? So that changes to a 1, but the rest of them remain the same. 1, 0, 0, 0, 0, 1, 1. And here we take the 1's complement. 0, 0, 1, 2, 3, 4, 0. And again, we have a sign bit is 1 that indicates negative. So in this case, we can just add the 1 to the 1's complement again, but again, the first one remains the same. Then we flip every other bit. 1, 1, 1, 1, 0, and a 1. So key idea. Let's point out here in our 2's complement system. 2's complement system. How do we represent a 0? We only have a positive 0. We don't have a negative 0. So you can show that to yourself. If you try to take the 2's complement of a 0, all zeros, you end up with 0. So we only have positive 0 in 2's complement. Okay, so what's the maximum number that can be represented in our 8-bit 2's complement system? So our 8-bit system, we have 1, 2, 3, 4, 5, 6, 7, 8 bits. The maximum number, of course, has to be positive, so our sign bit is going to be a 0. Well, maximum then, all our other bits are going to be equal to a 1. So that's our 1 plus 2 plus 4 plus 8 plus 16 plus 32 plus 64, which is equal to 127. This just indicates that it's positive, right? So we'll put parentheses around that. Or it's equal to 2 raised to the power of n minus 1, where our 8 bits, right? So our n is equal to 8. So that's our 2 to the 8 minus 1, or 2 to the 7 minus 1, 128 minus 1 is equal to 127. So that's our maximum number that can be represented. What's our minimum number that can be represented? Well, that minimum is going to be negative, right? So 1, 2, 3, 4, 5, 6, 7, 8. So we're going to have a 1 here, or at least we should expect that. But the minimum should be then if we try to take a negative 127. So if we take the 2's complement of this, you do end up with all the ones are going to remain the same, right? Till you get to the first 0, and it flips and it becomes a 1. So that is equal to negative 2 to the 7 minus 1, or equal to negative 127. So in an 8-bit system, our number n is going to be less than or equal to 127, greater than or equal to negative 127. We'll do capital N. That's our number n. Or it's going to be in general less than or equal to 2 to the n minus 1, 2 to the n minus 1 negative. Where n, right? N is the number of bits. N is the number of bits in the system. All right, the next 3 problems ask us to represent 80 and 64 in an 8-bit signed 2's complement, add them together, and then subtract them in signed 2's complement. So let's try to go through that, relatively quickly here. So we get 80, that's equal to 64 plus 16, or it's equal to, we'll do the 2 to the 6 plus 2 to the 4. So if we take our 8, we've got 8 bits, right? So our 64, and again, 0, 1, 2, 3, 4, 5, 6, 7, where we're using this most significant bit as a sign bit, so we can't use that. So that's good because 64 will fit. That's a 2 to the 6, we'll put a 1 there, and our 2 to the 4th, we'll put a 1 there, and everything else gets, right, a 0. And since it's a positive, we'll do a positive 80, that becomes a 0, right? So that's a positive 80 in signed 2's complement. And for our what is the other one? 64, that's easy enough, right? That's just a 1 and everything else. So it also has a 0 as a sign bit, and everything else, you know, is a 0, right? So that's positive 80, and that's positive 16 in our signed 2's complement. So if we want to add them together, then we'll take our 80, that's 0, 1, 0, 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0. We add them up, and those are all our zeros. 1, 0, 0, carry the 1, 1, and then we're carrying out a 0. So if we look at this number as our result, let's look at our carrying it out at the last stage again, and we look at this resulting number. Well, this number is clearly negative. Why do I know it's negative? Because it has a 1 for the sign bit. So what we have here is an overflow error. So if our carry in is not equal to carry out of the sign bit, then we have overflow error. Overflow error. And clearly, if we add 80 plus 64, right, that's 4. 8 plus 6 is 14. 4 carry the 1, so we end up with 144, and that's greater than the 127, right? 100. We said this is limited to, our n has got to be less than or equal to 127, negative 127. So we expect an overflow. How do we catch an overflow error? Right? We catch it by detecting that the carry in is not equal to the carry out of the sign bit. If we try to subtract them, we should be able to subtract them without an overflow error, right? So this was our 64, and we added them, right? So we added them. So if we want to subtract them, again, we'll put in our 80. That's our 0, 1, 0, 1, 0, 0, 0, 0. And then our negative 64, right? What's that? That's going to be the 2's complement here. So if we take our 2's complement of 64, all the zeros stay the same. 1, 2, 3, 4, 5, 6. The first 1 stays the same, and then we flip it, right? So that's a negative 64. You can also take the 1's complement and add 1, or do 2 to the 8th and subtract 1 from that. But that, you know, confirm to yourself that this is negative 64 in our in 2's complement, right? So it does give us the negative in the sign bit. Now we go ahead and we add those 0, 0, 0, 0, 1, 0, 0, carry the 1, 0, carry the 1, and now our carry in is equal to our carry out of the sign bit, right? So they're equal. So that's cool. So what do we end up with? We end up with 2 to the 5th. So this is equal to a 32. And in well, that's not right. It was equal to 32. That would be an error. So if we in fact subtract them, we get 6, and we get 7 minus 1, so it's 16. So I did that wrong, right? So that's our 2 to the 4th. That's equal to 16. So that's equal to 16. Check. All right, that's it for this video.